So, hello everyone. Welcome again to the One World Combinatorics on Words seminar. So our speaker today is Gabriele Fici from the University of Palermo, and he will speak to us about automatic sequences, Toeplitz words, and perfect shuffling.
Thank you, Nara. Thank you all the organizers for inviting me to give this talk. And I decided to give not the usual talk about my last paper. It's just a collection of remarks. I tried to look at something new for me because I'm not a specialist in automatic sequences. So sorry if what I'm saying is very well known for you. But I hope that at least for younger people, there will be something new, or at least a new point of view on known things. Okay, I cannot go on. Okay. Can you see my pointer? Yes, I suppose.
Yes.
Thanks. Okay, so the usual definition of right infinite word is a map from the natural numbers to a finite alphabet sigma. And this implies implicitly that we can describe this map in some way. But actually, we often use constructions of words. For example, we use substitutions, and we get purely morphic words, so fixed point of these substitutions. And we have a more general class that is a class of morphic words, which are obtained from a purely morphic word after applying letter-to-letter morphism, often from a larger alphabet to a smaller alphabet. And then we have another construction that is probably less used in the literature, which is the Toeplitz construction, which consists in starting from a sequence containing holes and filling the holes with another sequence. So let me go into details of the Toeplitz construction. Formally, a word x indexed from 0, so this is the infinite word x, is a Toeplitz word if for every n there exists a period p depending on n, so that x of n is equal to x n plus p, x of n plus 2p, and so on. But a Toeplitz word can be constructed from an infinite sequence of finite words, S1, S2, so on, over an alphabet sigma with an extra character denoting the whole, generally denoted by question mark, but there are also other symbols used in the literature. So these are what some people call partial words. And with some constraints, the first constraint is that each SI contains at least one occurrence of the question mark. And the second constraint is that infinitely many words in the sequence do not start with question mark. This is to prevent that the resulting word contains question marks. So the construction goes as follows. One starts from the periodic word S1 to the omega. So S1, S1, S1. And one then has to replace the subsequence of question marks by S2 to the omega. And this is the first iteration. And then one has to repeat this replacement for every SI in the sequence until one gets a word, a right infinite word, without occurrences of the question mark. So let's do an example. Suppose that our sequence is the following. Si is 0, 1 question mark if I is odd, and 1, 0 question mark if I is even. So there are two partial words alternating. So we start from 0, 1 question mark, 0, 1 question mark, 0, 1 question mark, and so on. And we replace the subsequence of question marks by 1, 0 question mark to the omega. So this question mark is replaced by 1, this is replaced by 0, this is replaced by question mark, and this is the second iteration of the construction. Then again, we replace the subsequence of question marks by, now we take 0, 1 question mark. So this is replaced by 0, this is replaced by 1, this is replaced by question mark, and this is the third iteration. You see that we have less and less occurrences of the question mark, and of course we take the limit, the usual limit, the same we use for defining the limit of substitutions, and we get in the right infinite word without question marks. What is this word for this particular example? So this word is called the Sierpinski gasket word, or I don't know if there is a general agreement on the name of this word, but it's a sequence in the online encyclopedia of integer sequences. It's a sequence A156595. And it is also the fixed point of the substitution that maps 0 to 011 and 1 to 010. So this is an example of the fact that the same right infinite word can be constructed with different constructions. And this is important because each of the constructions we have for an infinite word can give us particular properties of this word. For example, there is a theorem by Bocuto and Carpi, quite recent, that says that if X is a Toeplitz word generated by a sequence of words Sn with the hypothesis that these words are primitives. Now, for example, in this case, one could do the same using, instead of 0, 1 question mark, the partial word 0, 1 question mark, 0, 1 question mark. But there is no point in using something that is not primitive in the sense of partial words. So with this assumption, we have that if the maximal length of the words, of the partial words in the sequence is k, then the Toeplitz word is k-free. So the maximal length of the partial words in the sequence is bound on the critical exponent of the word. So from this result, we have immediately that the previous word, the Sierpinski gasket word, is cube-free, because the partial words in the sequence have all length 3, which could not be immediate from the definition of the same word by substitution. So it's nice that we have different constructions for the same words. In particular, there is a class of Toeplitz words called paper folding words, which are those words such that this sequence of partial words ranges in this set of cardinality 2, 0 question mark, 1 question mark, and 1 question mark, 0 question mark for every I. But at least in this talk, we only consider simple Toeplitz words. That is, we assume that the associated sequence of partial words is periodic, or ultimately periodic, but short of replacing the first word in the sequence, one can assume that the sequence is periodic. So there are words that are fixed points of morphisms, words that are Toeplitz, words that are both, and words that are known. For example, here is a list of some very well-known words. We have the Tuemors word, which is the fixed point starting with 0 of this substitution. Okay, I will always assume that the first letter is of the word is the first letter of the substitution. So even if I don't say it explicitly, This is the fixed point of this substitution starting from the first letter, so 0. And two-morph word is purely morphic, but cannot be generated with the Toeplitz construction. Then we have the Fibonacci word, which is also a fixed point of a substitution, with the important difference that this substitution here is not uniform, in the sense that the images of the letters have different length, while for the two-morph word, the images of the letter have the same length, and this makes a crucial difference. Then we have the period doubling word, which is both substitutive and Toeplitz because it's generated by a constant sequence. So when I write here, since I'm supposing that the sequence of partial words is periodic, if I write just one partial word, I mean the constant sequence. If I write more than one, I mean the alternating sequence of the partial words. Another example is the regular paper folding word, which is which can be constructed from the Toeplitz pattern 0 question mark 1 question mark, but cannot be obtained from a substitution. Another paper folding word I want to mention is the alternate paper folding word, which is obtained alternating the two partial words 0 question mark 1 question mark and 1 question mark 0 question mark. Then we have the already mentioned Sierpinski gasket word and the Rudin-Shapiro or Golay-Rudin-Shapiro word. I will use the symbol RS, which is neither a purely morphic word nor a word that can be obtained from a Toeplitz construction. Another class of words we want to discuss is the class of automatic words. So we are interested in words that are related to the string that represents n in some base b, for example, b equal 2. So we are given a regular language L over the alphabet 0, 1 up to b minus 1. And we fix a partition A1, A2, A sigma of the set of states of a DFA accepting L. So we're not interested in this case, in accepting states and non-accepting states, but we partition the set of states in sigma parts. And then we feed this automaton with the BRE representation of n, for n ranging from 0 to infinity. So we read the string representing n in base b, and we take the letter associated with the state into which we end the reading of n. And these words are called B automatic. And there is a famous theorem of Cobham that says that these words are precisely the words that can be obtained from a fixed point of a B uniform morphism, eventually applying a coding. And it's well known that paper folding words are automatic if and only if they are simple. So this associated sequence of partial words is periodic. So in particular, since in this talk I will only consider binary automatic words, mainly binary automatic words. In the case of B equal 2, one can use a rational property of n and use the language representing this rational property for describing the automatic word. For example, if we consider the language of binary representations of n that contain an odd number of 1, then this defines the two-morph word, because we start from the binary representation of 0, and this does not contain an odd number of 1, so we write 0. Then the binary representation of 1 does contain an odd number 1, so we write 1, and so on. For example, what is the rational property defined in defining the Sierpinski gasket word we saw before? Well, it's this one. So the ternary representation of n ends with 102 or 122. So this is another description of the same word we have. And this description in terms of a rational property. Of course, there is an automaton behind, so this is why these are called automatic words. Another things I want to mention is the relation with the two-adic valuation of n. The two-adic valuation of n is the largest exponent of 2, such that 2 to this exponent divides n. And if we write n in base 2, this corresponds to the length of the longest 0 suffix of the binary representation of n. So for example, if we take 18 in base 2, it's 10010. So it ends with a sequence of of length 1 zeros. So the two-adic valuation is 1. And of course, this can be defined for every larger b in a similar way. So sometimes it's convenient to use the sequence of two-adic valuation of n to describe an automatic word. And the sequence itself of two-adic valuations of positive integers is very interesting from the combinatorial point of view. So these are the first few terms of R2, so the sequence of two-adic valuations of positive integers. And this word is, of course, over an infinite alphabet, and it has different names. It's called a ruler sequence, Z-mean word, Infini-Bonacci word. It's the lexicographically smallest square free word. After deleting all zeros, one obtains the isomorphic word R2 plus 1. So let me say that I use arithmetic on words in the following sense, that R2 plus 1 means I map plus 1 to each letter of R2, because I use letters that are digits. So I can use this arithmetic. So R2 plus 1 is just the word 1, 2, 1, 3, and so on. It's also a fixed point of an infinite morphism, where 0 is sent to 0, 1, 1 is sent to 0, 2, and in general, n minus 1 is sent to 0, n. And it can also be constructed from a Toeplitz construction by taking the sequence of partial words 0 question mark, 1 question mark, and question mark. So it's a kind of beautiful generalization to an infinite alphabet of what we discussed so far. Of course, we can do the same for any larger base. For example, the sequence of triadic valuations of positive integers is this one, and it's the lexicographically smallest cube free word. After deleting all zeros, one obtains the same word plus 1. It's a fixed point of an infinite morphism in which each letter is mapped to 0, 0, and the next letter. And as a Toeplitz word is generated by doubling the same we did before. So 0, 0, question mark, 1, 1, question mark, and so on. So of course, these properties still hold for every value of b. So this is just a table that highlights how some automatic words can be described in terms of the ruler sequence. So this is the list of binary representations of n. We start from n equal 1 in this case, and this is the ruler sequence. If we take this sequence modulo 2, we get the period doubling word. Another example, we can defend a regular paper folding word by taking the r plus 2 to the last digit. So for example, this is 1 because 0 plus 2, the second from right digit is 1. This is 1 because 1 plus 2, 3, the third from the right digit is 1, and so on. a curious remark is that also the Fibonacci word can be related to the ruler sequence. If we take the ruler sequence, but we skip the integers whose binary representation contains 0, 0, we get the Fibonacci word. If we skip those that contain 0, 0, 0, we obtain the Fibonacci word, and so on. This is why the ruler sequence is also called the infinite Fibonacci word. So coming back to automatic words, I start now from 0, and I choose a rational property of the binary representation of n. I think we all know that if we choose an odd number of ones in n, we get the 2 Morse word. And if we choose the following rational property, an odd number of 1 ones may be overlapping in n, we get the Rudin-Shapiro word. So for example, here we have no 1, 1, no 1, 1, no 1, 1. Here we have 1, so odd. And this is why we have 1 here. No 1, 1, no 1, 1, 1, so odd. So we have 1. Here we have 2 1 1s, 2 occurrences of 1 1. So this is even. And this is why we have 0 here. So in this sense, the Rudin-Shapiro word can be considered a generalization of the 2 Morse word. But as far as I can say, the 2 words do not have many combinatorial properties in common. They are quite different. And I will show you why in the next example. So let's take the 2 Morse word. Let's delete the first letter. And let's take blocks of length 2, consecutive blocks of length 2. And we take the sum. So here we have 1, 1. So sum is 2. 0, 1. Sum is 1. 0, 0. Sum is 0. 1, 1. Sum is 2. 0, 0. Sum is 0. And so on. What we get is this word, H. This word has different names. It's called whole word, 2 square free word, a variant of 2 Morse. And it's often defined as the fixed point of this morphism. Or sometimes it's defined as the sequence that counts the number of ones between 2 consecutive zeros in T. So if we take the first and the second 0, we have 2 ones. If we take the second and the third 0, we have 1, 1. If we take the third and the fourth 0, we have 0, 1. So we have this sequence. But as observed by Jean Berstel in 1979, H can be also obtained from a fixed point of a uniform morphism of length 2 after applying the coding that sends 0 and 3 to 1 and 1 to 0 and 2 to 2. So this description of the whole word shows that it is true automatic. So it's not immediate that this word is true automatic from the definition of this fixed point as a fixed point of this morphism, because this morphism is not uniform. But here I'm interested in the fact that this word, if you look at it, the 2's and the 0's alternate. So after a 2 there is a 0, after a 0 there is a 2. Okay, so what if we take it modulo 2? So we map all 2's to 0. What word do we obtain? Do you know the answer? I think most of you know the answer, but maybe not everybody. So we get the period doubling word. So in fact, there is also an inverse construction. Since I always forget this morphism, if I want to construct this word, I start from the period doubling word, and then I replace every other 2 by 0. Sorry, every other 0 by 2. So let's recap the construction. We skip the first letter. We take blocks of length 2. We take the sum. And then we take the sequence modulo 2, and we get the period doubling word. So the period doubling word is naturally associated with the 2 Morse word with this construction. There are also other constructions that highlight the relationship between the two-most word and the period doubling word. But what if we, instead of starting from the two-most word, we start from the Rudin-Shapiro word? What do we obtain? So let's do the same. Let's skip the first letter and take the sum of blocks of length 2. So we have 0, 1, 1, 0, 0, 2, and so on. So we get this sequence, which unfortunately is not in the online encyclopedia of integer sequences. And we take it modulo 2. What do we obtain if we take this sequence modulo 2? Well, we obtain the alternate paper folding word, which is a Toeplitz word obtained by alternating the patterns 0 question mark 1 question mark and 1 question mark 0 question mark. So in both cases, we have an automatic word, a true automatic word, which is not a Toeplitz word. We apply this construction and we get an automatic word that is a Toeplitz word. In this table, I just recap the construction. So I deleted 0 and I started from 1. So this is the two-most word. This is the sum of blocks of length 2, modulo 2, and the same for the Rudin-Shapiro word. So this is just to highlight the fact that different constructions can give different properties of the same words. But the focus of the talk is on perfect shuffling. So let me define what I mean by perfect shuffling. Let's start with an example. We take the two-most word and we obtain it as a perfect shuffling of two infinite words. So I mean that I take the subsequence of letters in even positions and the subsequence of letters in odd positions. And I get that the two-most word is the perfect shuffling of itself and its complement. So it's a solution of this equation, actually the only solution starting from 0 of this equation. And in general, I call x even and x odd the two words whose perfect shuffling yields x. So for any right infinite word, one can write x as the perfect shuffling of its even part and its odd part. So we are interested in this talk in describing x even and x odd for other automatic sequences. Let me just point out that it is well known, you can find it in the very nice book by Jean-Paul Alouche and Jeff Shalit about automatic sequences, that a word x is automatic if and only if the even part and the odd part are both automatic. That actually the same holds true for Toeplitz word. In fact, x is a Toeplitz word if and only if the even part and the odd part are both Toeplitz. So there is this nice property that is shared by automatic words and Toeplitz words involving the perfect shuffling. So for the two-most word, we have a very simple description in terms of the perfect shuffling. Now, T is equal to itself, perfect shuffling, its complement. What for other automatic words? For example, for the ruler word, we already observed that it is equal to 0 to the omega perfect shuffling itself plus 1. For the period doubling word, it's very easy to see that it is equal to 0 to the omega perfect shuffling with its complement. For the regular paper folding word, we have that it is equal to 0, 1 to the omega. So in regular fonts, I put the even part, and in boldface fonts, I put the odd part. And the odd part is the word itself. It's the paper folding word. And of course, for the alternate paper folding word, we have that it's the perfect shuffling of 0, 1 to the omega with its complement. So in all these cases, the equation with perfect shuffling yields a self-constructing rule, because suppose that you don't know the period doubling word, but you just have the equation. So from this equation, you can deduce the first term, which is 0, and the second term, which must be 1. And then you deduce the third term, and so on. So you can construct the word from the equation, because in all these cases, the equation involves either constants or the word itself or its complement. But this is not the general situation. For example, let's now look at the whole word. So what is the even part of the whole word? This subsequence 20020220. Can you recognize it? It is twice the complement of the two-morse word. Or if you want, it's the two-morse word written on the alphabet 20. And the odd part is this word 12111012, which is itself the perfect shuffling of 1 to the omega with h, with the word itself. So this is an example that shows that this equation with the perfect shuffling could be more complicated than in all the previous cases. Actually, the word x, which as per today is not yet in the online encyclopedia of integer sequence, it's the word 1 minus d, so the complement of the period doubling word. So x modulo 2 is 1 minus d, but more precisely, if you replace every other 0 by 2 in 1 minus d, you get this word x. So what about the Rudin-Shapiro word? I was surprised when I did the same for the Rudin-Shapiro word, actually. So if we take the morphism that maps 0 to 0, 1, 1 to 0, 2, 2 to 3, 1, 3 to 3, 2, and we consider its fixed point starting with 0, we obtain this word. Then after applying the coding that maps 0 and 1 to 0 and 2 and 3 to 1, we obtain the Rudin-Shapiro word. But what do we obtain if we apply another coding? The coding that sends 0 and 2 to 0 and 1 and 3 to 1. We obtain this other word that I call RS prime. And it's not in the online encyclopedia of integer sequences. So you could wonder why I consider this word RS prime. And the answer is because, so this is a witness that it's not in the OEIS. The reason is that if I consider the even and the odd part of the Rudin-Shapiro word, I get this this equation. RS is the perfect shuffling of itself with the word RS prime. And RS prime in turns is the perfect shuffling of RS and the complement of RS. So you could replace this equation here, and you get that Rudin-Shapiro word is the perfect shuffling of itself with its complement. So even in this case, we get a self-constructing rule using the perfect shuffling operator. And I claim that the sequence RS prime should be added to the OEIS just because it's the sequence of the parity of 1 1s in the binary expansions of odd integers, but also because it appears here in this equation. So now you can say, okay, this was easy because you started from 2 automatic words. So they come from morphism of length 2. So what happens if we consider 3 automatic words? Okay, now we need examples of 3 automatic words. Here are some. I consider, for example, these 3 words, ln2. ln2 is defined as the last non 2-digit in the ternary expansion of n. So we take the last digit of n if it is different from 2. Otherwise, we look at the preceding digit and so on. So for example, we have 0, 1, then the last digit is 2. So we pick this 0, 0, 1, then we take this 1, 0, 1, then here we have to skip these two choose, and we take this 0. The other example is usually called the Mephistophels word, which is another generalization of the two-Morse word. Recall that the two-Morse word can be defined by the rational property that the binary expansion of n as an odd number of ones. Here we take this rational property that the ternary expansion of n has an odd number of 2's, and we get this sequence 0, 0, 1, 0, 0, 1, 1, 1, and so on. Another example is the well-known Stewart choral word that Ian Stewart defined in his nice paper on Scientific American about non-ending chess games. And the rational property associated with the Stewart choral word is n ends in 2 and a sequence of ones. Okay, so let me describe these words and other words in the same terms we used for two automatic words. That is morphisms and Toeplitz construction. And we get this table. We get that ln2 is the fixed point of this uniform morphism, and it's a Toeplitz word generated by the constant sequence 0, 1 question mark. Then the Stewart choral word is the fixed point of this other substitution. Notice that they are very similar, and it's associated with the constant sequence of patterns 0 question mark 1. The Mephistophels word is also a fixed point of 3 uniform substitution, but it's the only word in the list that it's not the Toeplitz word. It cannot be generated by a Toeplitz pattern. Then we have the Sierpinski-Gasket word we introduced at the beginning of the talk. And this other word that I found in the online encyclopedia of integer sequence, but I could not give it a name. So I called it no name. So symbol NN. It's a fixed point of this substitution. 0 goes to 0, 1, 1, 1 goes to 0, 0, 1. And it can be obtained with the Toeplitz construction alternating 0 question mark 1 and 1 question mark 0. So a curious remark is that the Sierpinski-Gasket word can be obtained from the Mephistophels word by taking the sums modulo 2 of 2 consecutive letters. If you do the same starting from the two-Morse word, you get the complement of the period doubling word. So the same construction applied to the Mephistophels word yields the Sierpinski-Gasket word. Then all these words have critical exponent 3, but the Mephistophels words avoids 3 plus epsilon powers, but it contains arbitrarily long cubes. While all the other words in the list have very special properties in common. They all avoid cubes, and this is this can be seen from Boku-Doncarfi theorem because they are generated from a sequence of Toeplitz patterns of maximal length 3. They also avoid the patterns, so factors of the form XX, YY, XX. They contain 3 minus epsilon powers for every epsilon. And another, and they all have factor complexity 2n, while the Mephistophels word has complexity 4n minus 4. And maybe the most curious property is that all these words in this list share the same set of palindromic factors, which has cardinality 15, including the empty word, which is very small actually, because okay, it's known that there are aperiodic binary words containing a finite number of palindromes, for example, paper folding words. But the minimum number of palindromic factors of an aperiodic binary word is, I think, 11 or 13 if one imposes that the word is the set of factors is closed under reversal. So this is not optimal, but it's close to optimal. And even if these words have different factors, their set of palindromic factors is the same. So one other remark about the word ln2, last known two-digit, is that if we take a conjugate morphism, so it is the fixed point of this morphism, 0 goes to 0, 1, 0, 1 goes to 0, 1, 1. If we shift the images, we rotate the images by one letter, and we consider the morphism that sends 0 to 0, 0, 1 and 1 to 1, 0, 1, we get the word 0 ln2. So the same word, but with an extra 0 at the beginning, which is almost a Toeplitz word, in the sense that it can be generated by a constant sequence question mark 0, 1, but violating the condition that infinitely many words, partial words, do not start with question mark. So we can generate it with the Toeplitz construction, but in the end, we have to replace the first letter, which will be a question mark, by 0. And I found a paper by Sebastian Ferenczi in 1995, in which he observed that applying the morphism that sends 0 to 0 and 1 to 1, 0 to this word 0 ln2, one gets the Chacon word, which is another famous word, usually considered as a fixed point of non-primitive morphism, but still it is uniformly recurrent word. So another question is, why last non-two-digit? What about 0, 1, for example? So if we take the last non-two-digit in the ternary expansion of n, we get this word ln2. If we take the last non-zero digit, of course, we must start from n equal 1. But what we obtain is precisely the same word plus 1. So it's morphic, so it's isomorphic to ln2. And if we consider the last non-one digit, what we obtain is this word over the alphabet 0, 2, that is precisely twice the Stewart-Correll word. So there's no point in considering all these three words. So let's consider the perfect shuffling. Actually, in the case of the Mephisto-Waltz word, I could find the only result existing in the literature for this problem. In fact, in 2005, Narad, Jeff, and Mingwei described the even and the odd part of the Mephisto-Waltz word. They could give a construction in terms of morphism, and the words they obtained have the property that they avoid large squares, while the Mephisto-Waltz contains arbitrarily large cubes. And this answered a question raised in 1979 by Prodinger and Urbanek. So of course, you know that binary word cannot avoid squares, but these words avoid squares of length larger than 4. So the only squares they contain are 0, 0, 1, 1, 0, 1, 0, 1, and 1, 0, 1, 0. For the word ln2, we have that it's the perfect shuffling of the Stewart-Correll word with the complement of ln2. And for the Sierpinski gasket word, we have that it's the perfect shuffling of this no-name word with the complement of the Sierpinski gasket word. So it seems that all these three automatic words in the list are related one to each other by some combinatorics. For the Stewart-Corral word, we have that the even part is a Toeplitz word obtained by alternating the partial words 0, 1, question mark, and question mark 0, 1. And as a fixed point of a morphism, it's a fixed point of a 9 uniform morphism. And for the odd part, it's obtained with Toeplitz construction alternating question mark 0, 1 and 0, 1 question mark. And it looks very similar to the situation that we have for this no-name word. Look at these similarities. The result is very similar for the no-name word, but the partial words in the Toeplitz construction are 0, 1 question mark and question mark 1, 0 instead of question mark 0, 1 for the even part, and question mark 0, 1 and 1, 0 question mark instead of 0, 1 question mark for the odd part. And both are fixed point of 9 uniform morphisms. So this is all. I want to conclude with some questions and further directions. First of all, I don't know if this is known, but can we characterize the intersection of the sets of automatic words and Toeplitz words? Because these two classes are very interesting and they have a lot of common properties. For example, in the case of paper folding words, we have this nice characterization of the intersection, but what can we tell in general? What other classes of words are closed under perfect shuffle? For example, we observed that a word is automatic if and only if its even and its odd part are automatic. The same for Toeplitz words. But for example, this is no longer true for Sturmian words. For example, the even part of the Fibonacci word is in the EIS, and it starts with 0011, so it's not Sturmian. Also, it seems that there is some relationship between the factor complexities of the three words involved in an equation of the form x equal perfect shuffling on y and z. And the last remark is that all the properties I mentioned for the words in the list of Toeplitz 3 automatic words, that is critical exponent 3, factor complexity 2n, the same 15 palindromic factors, actually seem common to this class of Toeplitz words. The Toeplitz words generated by a sequence of patterns in the set ABC, such that ABC is equal to 0, 1 question mark. So in other terms, every partial word made by one occurrence of 0, 1 occurrence of 1, and 1 occurrence of question mark in any order. So it seems that this class of Toeplitz words deserves more investigation. And I'm done. Thank you.
Oh, thank you very much, Gabriele. Does anyone have any questions for Gabriele?
Jean-Paul? I cannot hear you.
Yeah, I think there is a paper by Julien Cassani, if I'm not mistaken, linking somehow automaticity and Toeplitzity. Am I right? I mean, I wrote something myself, but on a very particular case in the 80s. But I think there is a paper by Julien and probably Karim Mekil.
Yes, but it's not. Yeah, there are results on on the question I raised, but I couldn't find a characterization of the intersection.
Probably not a characterization, you're right. Probably not. Yeah, okay. And there's also a paper by Michel Koskas that you might have seen, but I think it doesn't give a complete characterization either.
Yeah, I found quite interesting that many of the properties I discussed in this talk are shared by the two classes of words.
Does anyone else have any questions for Gabriele?
Could you give some reference to get introduced to Toeplitz words? Well, actually, I don't know if there is one reference from which to start, but there is a collection of papers on the subject, and I think that all deserve to be read. So Googling Toeplitz words is probably the best. But I want to mention one in particular, one paper by Jean-Paul Alouche, which appeared in recreational math journal.
No, in l'enseignement mathématique, and the other author is Roland Bacher. And in this paper, there is the original reference, I forgot, which is by Susan whatever, where I think this is one of the first papers, maybe not the first, but one of the first papers on Toeplitzity, if I'm not mistaken. I can't find right now the name of this author, but it is cited in the paper with Bacher.
Mm-hmm. I think that for some reason there are much more papers on automatic words, Sturmian words, than on Toeplitz words, because Toeplitz words I think have been considered always very close to periodic and in some sense less interesting than other words, but to me they are very interesting.
Have you written something, or have you some sort of abstract or some sort of?
Not yet. I just collected some remarks and computations and experiments. But yeah, the plan is to organize this stuff into maybe a paper for Journal of Integer Sequences, because I found that there are things that could be added to the online encyclopedia of integer sequences related to this talk.
Right.
Are there any other questions? If not, thank